Okay, so let me briefly introduce myself. Yeah, today we will talk about the distributed systems. I will try to make it fast, fun, and useful for all of you. So let me introduce myself. My name is Andriy, and here is my contacts. So if you will have any questions or just to collaborate according to work questions, no problem. Join and follow me. I am a founder of Jaffer company, and I am co-founder of 12.0 projects. It's a startup. I am part of program commit of Morning at Logica. It's a Lviv local community. So I invite you, all of you, become a speaker or probably just a participant. It's very interesting. Also, I'm a part of program commit of Devoxx. So if there was some shitty talks, you can, who did it, yeah? And of course, I'm an organizer of Java Day Lviv, not Java Days that become a Devoxx, but Java Day Lviv, that will take a place in Lviv at February 23. So you are welcome for this. And before we start, let me check the audience. How much of you know about distributed systems? Who work with this? A lot of people. Okay, who understand the openness principle of goals of distributed systems? Right, one person. I guess it would be interesting for another. Okay, the content is pretty simple. I will keep it simple, fun, and fast. So, first of all, we need to understand what the distributed system is and how to classify them. Then another question is why? Why we need them? Which exact tasks or other things required to be executed or distributed in such systems? The another way is to how we can build the distributed systems. That's actually 3 questions, and we will try to give an answer during this talk. So, fun, fast, and useful. Let's go. What the distributed system is. And to answer these questions, it's not a quick or easy questions. And the answer also can be a 1 sentence or 1 slide. To make it properly, we need to figure out a few things. The distributed system has features, it has goals, and it has challenges. So we will go one by one to explain all these 3 pieces. First of all, features. Which exact features the distributed system has? First of all, it's always multi-instances system. So it can't be 1 instance. It's always multiple instances. That's pretty easy. All of them work asynchronously. They execute tasks asynchronously, so they are parallel, actually. All of them can be located in different time zones. It's not something located in 1 machine, few threads, or something like that. It can be absolutely distributed around the world, different data centers. That's another feature. And it can share a resource. That's very important because, for example, microservices, they do not allow you to share resources. If you have user service, then user service can own only data related to this user resource, and that's it. But with distributed system, you can share resource. That's okay, definitely. That's the features that describe that this system is distributed. Goals. There are few goals that absolutely all distributed systems try to follow. And first of all, it's a transparency. It's like a galaxy, yeah? We all know that galaxy contains a lot of suns, stars, and, planets, etc. But when we talk about this, we just say galaxy. And everyone understands what is in the behind, under the hood. The same with this system. We all understand that it's a complex system with a lot of instances, but when we talk about this, we say, oh, this is a cluster of Cassandra, this is a cluster of Apache Spark, and that's it, that's enough, because your system should be transparent for everyone. Then, another goal, it's an openness. My question was about the openness. That means that your cluster should be ready to be configured, reconfigured, and changed any things in runtime, and it shouldn't require to restart the system. It can require restart the single instance, but not the whole system. So that's the openness. Absolutely all distributed systems should follow this. Another one is reliability, and we all understand what it means. When we have a cluster and you send some data or you send some task to be executed and something bad happened, it may happen. Network is not present or something other crashes happened in this system, you should rely that your data will be saved or your task will still be executed. And for this, we should rely for these systems. So distributed system require to be reliable for you. Another one is performance. That's when you have a complex task and the cluster where this task can be distributed and executed in parallel. The performance is a key goal of each distributed system, because if this system is not give you a performance, probably you not need this, right? Another one is scalability. When we have a cluster, it should be able to scale when we need this, and it should be able to downscale. That's the reason. Without this goal, it's not reasonable to use distributed system. We need this, and the systems should follow these goals. So we talk about transparency, openness, reliability, performance, and scalability. All these goals is required. And if systems that you are using, try to use or try to build, does not have at least one of these points, there are no reason. And the last point that can classify that this system is really distributed is the challenges. Because why? Because we need this. Actually, we don't need this, but actually all distributed systems have this. And first challenge is security. Why? Because of evil. Because every time if you have a cluster, it can be broke by someone, it can be hacked, the DOS, etc. A lot of issues may happen because you have a lot of instances. You need to monitor them, you need to provide a strong security. That's the challenge that always will be present if you have a distributed system. Another one is the fault tolerant. Because if you have a cluster and some nodes, some instances, sometime may burn out from your cluster. And it shouldn't be a reason to fail. It shouldn't be a reason to lose the data or your tasks. So that's a challenge. And if you understand this, you will point your attention to make a proper configuration or use the proper protocols of communication. We will talk about this. And the last one is coordination. If you have a cluster and we put the data to this, how to find the right path? How to find exact place for this data or for these tasks? How to find shortest way or probably the most reliable, something like this. So the security, fault tolerance, and actually coordination. 3 challenges that always will be present in absolutely all distributed systems, and there are no way. And you should solve this problem every day. When you develop this, or probably you are using some distributed system, you should understand and solve these problems. So what is distributed system? It's a set of features, it's a set of goals, and of course there are challenges. We talked about some main points. Of course, some different particular business cases require different points for features, goals, or challenges. But that was a main things that explained that this system is distributed. And that's it, actually. Why? Why we need this? If it's so complex, probably we don't need this. But actually, there are at least two classic tasks that can be solved distributively much better than another way. And we will talk about these 2 main points. First of all, it's data processing, not storing. We are not talking about some big data and our challenge is to save this somewhere, to store this. That's not a problem. That's solvable. But how to process this data? That's the issue. And another one is a task execution. If you have a lot of tasks, if you have some limitation of time, and you need to do this immediately, the best way is to distribute this. So, which classical task for data processing do you know? Probably you all know the MapReduce. Who don't know what it means? Few persons. So MapReduce is a classical interface, actually, because implementations, there are a lot of implementation by Hadoop, etc. So it's an interface that told us how to efficiently decrease huge amount of data and receive the exact result that you needed. But how many of you know which interface MapReduce extends? So MapReduce is also interface, but this interface is a child of some another interface. Is there someone who know? Distributed acyclic graph. That's the root case that was extended by MapReduce. And to prove this, I will show this actually example. This distributed acyclic graph told us next. If we have huge amount of data, some source, we should tokenize it. We should split it by tokens. Then we should accumulate this data, combine, and then we will receive results. Pretty easy? Probably no. Let's talk a little bit more deeper. Which classical task you probably know for MapReduce? Of course, count of words. That's really classical task. Count of words, how it will work with this distributed acyclic graph. If we have a source, what it means for us, we have lines of text, that's it. If we do tokenization, what we are doing? We split this text by exact words, so we receive the tokens. Then we accumulate them, and it means that we set for each particular token a pair, like a count, and by default it's 0 or 1, actually 1. And then we combine, so we're doing reduce. And as a result, we received a unique set of words with a count. That's it. That's why MapReduce is extended by distributed acyclic graph. And that's why this should be, and by design, implemented distributively, so on distributed system. How about task execution? Having distributed system, it's pretty easy to have a cluster and some job coordinator that will send us jobs that you as a user or owner of this data center will set up, and that's it. So it's also pretty easy. I guess it's understandable. But in this type of cluster, we should have this job coordinator. Actually, it's one of our challenges that we will talk a little bit later, but actually we should have this. Which another way to solve task execution we may have? We may have a cluster which will be self-organized. And in this way, we will have a context, and each particular instance in our cluster will pick up a job, execute this, and provide a result. Pretty easy. So why we need this? Actually, instead of these two classical tasks, because of scalability. We need this scalability, right? Because if we don't need this, then I don't know what we are doing. Probably it's some tool executed on some desktop, and that's it. We don't need a scalability for this. But if you talk about some network, about any application, web application, sometimes it required to be extended, because sometimes you have more users than usually. And sometimes, of course, decreased. Another one, reliability. We should rely for our system, because if it's only one instance and it's die, then that's it. We do not have nothing. And the speed. We try to reach better performance. We try to execute our tasks faster than it's usually. If we don't have all these 3 points, probably the distributed system is not a correct way for us. And how? If you understand what it is, why we need this, how we can implement this from the scratch, actually. That's pretty easy. And to do this, we can say that we need few things. First of all, of course, the cluster. We should build this, we should care about this. We should care about communication. That's a very important part. We should care about coordination, how we will deliver our messages, how we can detect the failures and handle this correctly. Actually, how we will solve the consensus, how we will solve conflicts, actually. Yeah? We need some consensus algorithm that will provide this functionality for us. Let's take a look closer on all of these parts. If you talk about the cluster, one type of this cluster can be a cluster with a master node. And this master node will interact with your client. Your client will send data or tasks, any kind of messages, and the master node will deliver it to another node in your cluster. And the problem is, what happened if we lost this master? That's the challenge for us. We should keep this in mind, and at least we should have few masters in our cluster. There is another way. We already know that there are some clusters called like ring clusters, where all of instances are the same node. And in this way, we have a state. All of these instances interact with the state, and everything looks okay, right? No single point of failure. At least this state. How to care about this? How to make sure that this state is consistent for all of your instances in your distributed system? That's the problem. And to solve this and previous one, we should care about communication. Communication, that's really one of the major points in your cluster. First of all, you should care about your data format. It can be absolutely different. It can be JSON, it can be binary data, a lot of other type of resources. Why not? You should decide which one will be better for you, which one will be easier to send through the network. So that's the one point. Another point of communication is the routing. How to find the correct way for your message. How to deliver it in the fastest way, and the shortened way, and the robust way. To grant that this message won't be lost. That's important. Acknowledgement. Very easy stuff, but you should care about this as well. If you have two instances that interact with each with other, we should send an acknowledgement every time. That provides some guarantees that this message was delivered and you are safe. That's important part. Timeouts and retries. Each time when you make a message, it can fail. That's happened, that's okay. You should care about this, you should handle this properly with some retries, exponential, or probably just with some period of time, and repeat this interaction. Only that time, in that time, you will provide a guarantee for your end users that this message was delivered. And direction. If you have an instance and some client send you a message, which one of the other instances you will select? That's the issue that also can be solved by some protocol, by some implementation in your distributed network. So, the last one is the sequence. As we understand, we have a cluster and there are always something happened. Even you don't send anything to this. It should interact, it should update state. Which sequence you will select, which flow you will implement for this. That's important. And to do this, people already implement a lot of things. And the most popular one is an epidemic algorithm called gossip. And to explain how it works, I prepared some animation for you. And it means like when one node knows something, it selects some another nodes, it talks to them, and it's like a rumor shared around your cluster. And in some short period of time, all of your instances will be up to date. That's like a rumor. That's one of the best algorithms, and actually you can use it. It solves a lot of problems of communication. Another one, when we talk about the building of distributed system, is in coordination. To do this, there are two major parts. Data distribution, how to distribute your data, how to distribute your tasks, and how to select neighborhoods. who will be my neighborhoods, because the efficient way is to talk to your neighborhoods, not with some instance that's located in different data center, probably in different location. That's two classical problem, and to solve this, to solve actual distributed data distribution, we should understand that all your data is a some range from minus something to plus something, and usually that range is a long type. If we know this, if we understand that all data have some beginning and some end, there are no infinity, unfortunately, we can split this range correctly and assign to your particular instances. And then you can manage it. How to select neighborhoods? And that's also nothing new. We already have such algorithms called snitch functions. Is there anyone who knows what snitch means? Some guesses? What is? Probably this picture will help. Harry Potter. That's not a Harry Potter. Snitch is a man who knows something interesting about you and can tell to someone else. Probably for some profit. I don't know. That's a snitch. And how they works, these snitch functions? Very easy. When your cluster communicates through this communication protocol, for example, gossip, the interactions is continuously executed. And when one instance talks to another one, it can measure, for example, latency. And this latency has a value. And I remember this latency, yeah? Then another instance will talk to some other instance and measure the same. And then they can share this experience. And in some period of time, the cluster will understand who is who, on which latency, and who is my neighbor. In this example, my neighbor will be those nodes who is the closest to me according to latency. But there are a lot of algorithms that can provide the snitch functionality for you. The next point is a failure detection. This is very important because without this, actually nothing may happen. And first approach is the exact value, just true or false. The another one is continuous value that always can be changed. To look it more close, exact failure, when your instances talking to each other and something bad happened, then the node which are not responding will be removed from the cluster, and that's it forever. No way out. That's exact failure value. With another approach, continuous failure value, when instances talking to each other and something bad happened, the instance who initiate this communication make a note. I can't trust to this instance. Probably they burn out from the cluster. But if in some period of time, some another instance, because we are talking about distributed systems, there are a lot of instances, will talk to the same node and the communication will be successful, the state will be shared in some period of time between all nodes, and this flag, this node, will be removed. And the cluster will believe and will trust this instance again. And the last very important part when we talked about building of distributed network is the consensus. Collisions and conflicts always happened. And that's true, because even you have a lot of clients and they do changes at the same time. That's it, that's a collision, because you have similar version of the data, or probably changed in short period of time, and you need to select which one you should trust. And to fix this, there are two common approaches. One is the raft, another one is the primary backup. Raft, a little bit slower, but it's grant consistency, because it's directly work with your disk, with your HDD or SSD. And primary backup is very fast, but it works with memory. So you can lose data if your server at least will be restarted. To take closer raft, when the client sent message to your instance, actually it put this absolutely to your disk space. And then, at least when it's happened, the successful message sent back to your client, and you understand that operation was successful. And you know that everything may happen. The server can be restarted or something like that, but data won't be lost. You can rely to this protocol, but it's slow. And to tell, but anyway, conflicts and collisions may happen. How it resolve? It resolved because Raft protocol always has a leader. It has a follower and it has a candidate. So if any collision happens, only leader provides the decision, which version of data you can rely. But what's happened if leader will go on? Yeah, let's take a look. Every time leader make a sync calls to the followers, just to be sure that it's present. And of course, it replicates data. If something happened and no sync request in some period of time, then followers who are absolutely copy of this leader make a call to all candidates and says, please, I need election. I need a new leader because this one is not responding to me. In that case, candidate start election and trying to reach this leader. And if leader is reachable, at least for some one instance, the leader will decide who one from the candidates will become a new leader. But it should decide a new leader because leader election was started and that's it. If no one of candidate will ping the leader and leader is totally out of the cluster, then it makes call to the follower, and the first one who will reach the follower who initializes the leader election will become a leader. And then this follower will send back the acknowledgement request and say, okay, you said me that I'm going to leaders and I will do you a next follower. That's it. Like a politician, yeah, something like this. And the next protocol is primary backup. In this way, it's pretty much easier because when you make a data request to your instance, it just left it in memory. Pretty fast, but as I said, sometimes it may be not consistent. If you lost this data, then it's not present on your disk, and that's it. So how it works actually and how it resolves the conflicts. We should have at least one client who interacts with us, who can send us data or tasks. We should have a primary instance who actually also the one instance who decide where is true, where is false, which data you can rely and which not. And we have a backup. How it works? Actually, all time, continuously in some period of time, primary instance send a sync calls to backup just to make sure that I'm alive, everything okay. If client send a request, send some data or tasks, primary backup, primary instance receive this and send the same data to the backup. So make a copy of itself. And only then response will be sent to the client as everything okay, your request successful, you can trust me. In some period of time, if primary stop send sync request, backup will say, now I'm primary, and some other instance will be selected as a backup. That's it, how the conflicts solved in this system. So, how to build these distributed systems? We should care about cluster. We should remind that communication is not easy question and there are no way out. A lot of points related to communication need to be solved by you. Coordination, another question. Failure detections. There are a lot of algorithms. You can also implement your own, but it's an important point in terms of distributed systems when you're trying to build your system or try to configure someone already existed. And the consensus algorithm, very important part. And right now we came to the demo. I tried to do this fun, so I hope you will like this. And to make this demo, I will use the framework called Atomix. Probably someone already know about this. So actually Atomix is just a set of tools, set of protocols, and different solutions for distributed systems that are packed to one box and provided to you like a framework. And you, having this Atomix, you can build your own distributed systems. And that's it. So it's not a complete solution. It do not provide to you some exact value, exact business case. It's just a tool like a, I don't know, like a Spring Boot, just a tool. What you're going to build on this? It's depending on your business case. The same with Atomix. It's just a tool. And right now, we will build something. And we will build Galaxy Race. So, and we will try to do this very fun. What we need to build this Galaxy Race? First of all, we need a Galaxy, right? And probably you already know that this Galaxy will be a master instance in our cluster, because without this, we can do nothing. And it would be bad demo because I will have only one instance, but you understand that there are a lot of Galaxies. So actually, you know what to do with this. In real life, you need much more than one instance of your master instance. And we need a racer. That's another project, that's another instance that we are going to execute, and we will see what's going to happen with this. And if you build this correctly, we will execute a lot of the same instances because it's distributed system, right? We can scale it as we need. We can downscale and upscale without any problems. So we can execute a lot of instances of our racer, and it should work without any magic in code or, I don't know, providing IP addresses, etc. So, what we need else to do this? Actually, Galaxy, it would be one project. The racer, which will be executed multiple times, will be second project in our system. What we need else? We need some resources, right? Because it's distributed system. We need to share the state. We need to share some data. The first resource that we will introduce will be type of Boolean, and it would be distributed Boolean. And this only to say when the race start and when the race finished. Only this will be contained in this resource. Another one will be a map, distributed map, and it's only because we need to know the racer name and the racer state. And actually, what means the racer state? It will be some value from 0, because initial value for each of racer will be 0, and from 0 till infinity until the race will be finished. So actually it would be randomly add some number to finish this race before other racers. What else we need for this? Of course we need the front end, because without front end it would be really hard to understand what's going on in this distributed system, right? Right? Okay, showtime. We will try to do this, and I hope this would be pretty fun. As I promised, we have only, sorry, not so easy, because I need to switch this in this way. Okay. Wow, it's so slow. And I don't see this in my... Okay, I will take a look there. So, we have two projects, the Galaxy and the Racer. And what we need to build the cluster with these two projects only. First of all, let's take a look what Galaxy is inside. And, wow, that's hard. And what we have inside, we have configuration. And this configuration is pretty simple, at least should be. It has a cluster configuration. What is inside? Inside is only one bin. It's a Spring project. Only one bin that's called Atomix. And this is an instance of this Atomix. To configure this, we need only a few things. We need to know the name of this instance. We should provide a unique ID for this one. We should have a port to execute, to start this instance on some port. We are enabling multicasting. This allows us to build a cluster that will learn ecosystem automatically. So with this parameter, we don't need to know how much other instances we will have, so everything will be automatically. And we are using some profiles. We will talk about this very briefly, but later. So exactly this way save me to not doing not pretty cool stuff like providing consensus algorithm, communication protocol, etc. So if I provide this profile, that's okay. But I will show you that everything is there, and all points that we discussed all this previous time make sense because it works exactly inside this. So what we have else in this project? We have another configuration called resources, and there are only two resources that I promised. There are atomic value boolean, that is distributed value, and atomic map. Why atomic? Because we need to make a grant that it will be absolutely consistent when the value will be changed on all instances. And that's it. There are nothing else except controllers and service. Controllers, pretty common stuff. It's related to Spring. It's not about our demo, but the service I can show you. That's it. Nothing special. We just receive some comments and we set this to our values. For example, if we need a start race, we set true value to this race status value. The same with stop, the same with when we need a reset. So we just go through all states and set the actual state of each particular racer to 0, just to make the race from the beginning. So that was actually Galaxy. Let's take a look what we have with our racer. And actually there are nothing else except cluster configuration. Okay, the same, pretty similar, except only one. Right now I do not provide the profile because it's not needed. Because if this instance will join the cluster, it will already receive information which communication protocol we are using, which exact consensus algorithm we are using. So I don't need to provide this on each instance. If I know that this one will be connected to the cluster, and that's it. So that's pretty simple. The same with resource. Only these resources that we already discussed. And probably more logic in service, because this one is pretty interesting. So when we start, we have this post construct. We add a listener to the race status. And if this value will be changed, it automatically will call this listener and say, okay, the race status changed, do something. And if we go into this one, it will decide start or stop the race. And if we talk about starting the race, so it has a scheduler that schedule next and next step, which just randomly add a value to already existed. That's it, nothing else. It's a random race, actually. So let's take a look how it looks in real life. I will go from the presentation mode because I need to start the project, and actually it is really not useful to do this using that monitor. So, starting the Galaxy, let's see what's happened. Am I pressed this? Yes. Okay, the Spring Boot application starting pretty fast. Yeah. Right now I need to show you what we have in our Galaxy. And to do this, I need to put the browser into that window. Sorry for this, it's not expectable actually. So we will restart and we see our Galaxy. So that's that one instance that has a UI interface. So actually that's a couple of JavaScript inside, but it takes a state from our cluster and try to provide it here. Right now we didn't start any racer, so the Galaxy is empty. Okay, let's start at least one racer. We will see what's happened. Racer 1, somewhere here. Hope it would be fast. It should be fast at least. It started. Let's take a look here. Yeah, we have one racer and we are ready to start the race. But it's not interesting with only one. And actually that's not interesting because what's happening with the cluster at this point? Let's take a look closer. And if we take a look on our galaxy, we will see that in the end, when we start our racer, I'm not sure if it's visible because it's at the bottom. And actually, probably no. At the bottom, we will see that the Java racer is joining this cluster. So everything happened automatically. I didn't provide any IP addresses. I'm just starting the instances on different ports because I'm using the single machine, but everything going to discover the ecosystem automatically. Let's run another instances and start our race. Racer, 2. Okay. This one. And probably racer 3 immediately, just to save our time. That's it. So, we have 3 racers, I guess it's enough, and Fairy to start the race. Okay, it started. Let's refresh the browser. That's it. So, Java, Scala, and Kotlin. Any points? Let's go. And no sound. There should be a sound which you do not hear. Pretty bad. Java racer wins. Is there any chance to make a sound for us? Bad. Okay, we can restart this. Try again, just to make sure that something really happened. Probably if I will switch off, I don't know, because there are so cute sound. Okay, now the Scala racer win. So, what's happened on the background? Let's take a look. There is our racers, and what's happened? For example, this racer 3. Oops. It just generated values because at the beginning, I guess the race was, wow, that's not usable. Somewhere there, not sure where. Somewhere here. Yeah. So when the Kotlin racer registered, after some period of time when we press start, it received a message that you should start, and it started. And it started to generate random value between 0 and 3. So we always have the incrementation by 0 or 2 or 3. That's it, or 1. So, but this is a distributed system, and we need to prove this. I will restart the race. And for example, right now I need to extend this cluster. And I will start one more node. Why not? If you talk about this distributed system, right, that shouldn't be a problem. And actually that's it, because using Atomix, yeah, we are encapsulating all of these problems, but knowing this, you can create a better application, because what it is, it's just a demo, but in real life, you need care on this manually. Right now we have one more racer called Groovy, and let's check what's happened. No sound. Okay. Haha, Java win. Okay, so actually, yeah. Just a second, sorry for this. Probably. This one. Okay, probably right now it will be with sound. we need to hear this. Yeah.
Y'all gon' make me lose my mind. Up in here, up in here. Y'all gon' make me go all out. Up in here, up in here. Y'all gon' make me act a fool. Up in here, up in here. Y'all gon' make me lose my cool.
Come on. Something happened. Oh, I don't know. But groovy win. Okay, fair enough. So I hope you like this, because actually it was easy, right? Just a couple lines of the code and that's it. You're done it. But yes. Yeah, I didn't try it actually. I tried to use Docker for this, and that was only once, and when the Atomix was pretty old, and all stuff need to be configured manually.
Because I know that Docker does Docker network or Kubernetes network doesn't allow you to multicast.
Multicasting, right? That's a new version of Atomix, and I didn't try the multicasting there. But with old Atomix, you should provide IP addresses all the instances.
Yes, with manual configuration, it should work, because I have the same problem with the bridged networks and
Right.
distributed systems that
Right.
it only
Highly
supports
possible.
manual configuration. But
I agree.
manual configuration
Yes.
is not a way to go.
Yeah, thank you for this notes. So, the summary, actually. We learn what the distributed system is, and hope you understand that there are no one answer for these complicated questions. So, there are a lot of things, a lot of features, goals, challenges, and we need to understand this, because when we're choosing some distributed system, we should weigh all pluses and minuses, pros and cons. We should understand this, which particular business case you're trying to solve. And will this selected or preferred distributed system solve this okay? Or probably you need to do something, some tuning of this, or probably change the technology. Why we need this, that should be pretty clear. At least 2 or probably much more classical tasks can be solved much more efficiently if you distribute this around the cluster. And how? How we can implement this? That's actually and easy and hard at the same time, because a lot of things are encapsulated inside. The communication, the file detection, all other things. But using the proper tools, you can at least do not care about this for some period of time. But of course, if you're trying to solve the real world life problem, then you need to care about this. And everything is present inside. You can configure it manually if you need this. The source code of this demo is located here, so you can play with this if you like this. I have to say thank you for Nick Mukherchan for the background that you saw. I'm not the front-end guy, so that was not my work, but he allowed me to use this. Some resources that I use for this, and thank you all that you came to me and listened to this talk.